Hi, this is an example problem from Chapter 18 on the electric field of a parallel plate capacitor. Pause for a moment and read the question. So we show a profile view of two plates, and they're charged equally and oppositely with electric charge. This is the general setup for a parallel plate capacitor. And we also know what the charge density is here. It's given to us right here. Notice that that's coulombs per meter squared. So for each meter squared of area, you get so many coulombs of charge on there. Now the positive one, they're positive, of course. The negative one, it's a net negative charge per meter squared. First part, it says draw the electric field lines inside the parallel plate capacitor. Well, for a parallel plate capacitor, we know that it's a uniform electric field. It means same value for E, same direction, same field strength, magnitude, anywhere inside the parallel plate capacitor. So we can go ahead and draw these. Remember that field lines, they begin on positive charges and they end on negative charges. So if I want to draw these, we can go ahead and start here on a positive charge, not inside the metal, but right from the surface where the charge is to the other surface of the metal. We go ahead and draw these along. And in fact, we can see that this is what they're all going to look like, right? And the last one starts on positive charge, ends on a negative charge. Now we need to get the directions correct here, right? So let's go ahead and orient the directions on these guys. We know that they flow from plus to minus, so they're going to look like this. And so now we've drawn our electric field lines, and this is what we were asked to do in part A here. For part B, it says calculate the strength of the electric field between the plates. Now, to do that, our source charges here, of course, the positives and negatives on the plates, they're not point charges. We can't use that old formula that we use for the electric field of a point charge. However, for a parallel plate capacitor, there's an equation we can use. It tells us the magnitude of the electric field for a parallel plate capacitor depends on the charge density, surface charge density, divided by a electrical constant epsilon naught, which is just a number that we look up. In this case, and this is magnitude. If it's, it should be positive anyways, but let's go ahead and write this down. So 1.5 times 10 to the minus 9th coulombs per meter squared. And this constant epsilon naught, which is related to Coulomb's constant K, it's equal to 8.85 times 10 to the minus 12th Coulomb squared per Newton times meter squared. And when we go ahead and do those cancel coulombs, there's 1 coulomb left on the bottom. We cancel out the meters squared, and when we're done with that, we'll see what the units are. So this comes out to a value about 169 newtons per coulomb. And that makes sense because we have, essentially, if we think of the units here, we've got 1 divided by coulombs over newtons, and that's actually equal to a newton per coulomb. In part B, we're asked to calculate the electric force exerted on an electron placed between the plates. Use a plus or minus sign to indicate the direction. So we're going to go ahead and place an electron. Does it matter where I put the electron between the plates? It doesn't matter because this electric field has the same value anywhere in between the plates. We know that because the electric field lines, they're equally spaced, right? From here to here is the same distance everywhere, and they all point in the same direction. Therefore, this is a constant electric field, same value everywhere. All right, so I'm going to go ahead and choose to put the electron, let's say, maybe right here. What does the electric field look like at that point? Well, let me go ahead and draw it. I'm going to use a purple arrow. And the electric field is always tangent to the field line, and it originates at the point. So it's going to go from here in the direction of the field line, tangent to it, and that's the electric field at that point. Now we're going to go ahead and place a little electron there. I'll use a green for this. So there's our electron. What's the magnitude of the electric force exerted on the electron because it's in that field? Well, we can use the formula that relates force magnitude to electric field magnitude. In this case, we're using an electron. Let me write the full equation. Q times E. Now in this case, write Q, right? Q for an electron is equal to minus E, where E is the elementary charge. The absolute value of Q is just E multiplied by capital E, electric field value. So we've got elementary charge, 1.6 times 10 to the minus 19th coulombs, multiplied by the field strength. We get 169 newtons for each coulomb. If we calculate that, we're going to get an answer. 2.70 times 10 to the minus 17th newtons. And of course, we cancel out our coulombs to get those units in newtons. What does the force vector look like? That's the magnitude, right? So I guess I'm not quite done yet here. Need to get the direction. Well, we know that this is a negative charge placed in an electric field. The field vector points to the left, and since this is a negative charge, it will be opposite the direction of the electric field. So there's the force exerted on the electron. Of course, it makes sense because the electron is going to be repelled from the negatives on the left and attracted to the positives on the right. And when we want to write that as a vector, if we just want to use plus or minus to give the direction, then it's in the direction of the positive x-axis. So we can write plus 2.70 times 10 to the minus 17th newtons. There we go. Finally, for part D, if the electron is released from rest, what acceleration will it experience? So imagine you're holding it there. Somehow it's fixed in place there. If we release it, it's got a force that acts on it. It's going to experience an acceleration. And the way we can calculate that, well, we're going to use Newton's second law. So the acceleration is determined by the net force that acts on an object, in this case the electron, divided by the inertia, the mass of the electron. So this is for the electron. And in this case, if we want to just get the, well, we're good here. So in this case, the net force here is only the electric force. We're ignoring everything else here. And if we go ahead and put in the value of the net force, well, it's equal to this. Then we need to divide by the mass of the electron, the inertia. And that number, if we look it up, it's a very small value, 9.11 times 10 to the minus 31st kilograms. And if we calculate that, we end up with the number 2.97 times 10 to the 13th. This should be kilograms. No, it shouldn't. This should be meters per second squared. And we can check because what is a Newton per kilogram? Well, a Newton is a kilogram meter per second squared. Divide by the other kilogram. And in fact, we do end up with meters per second squared as we expect. And so here's our answer. Notice how the electric force on the electron in part C is very, very tiny, right? 10 to the minus 17th newtons. However, that force generates an enormous acceleration because the mass, the inertia, the resistance to acceleration of the electron, it's even smaller, 10 to the minus 31st kilograms.